Hello everyone. Welcome to the first video of week 2 in which we start with the theory of estimation. When one is collecting a dataset consisting of repeated measurements of a particular quantity, the precise outcomes of these measurements beforehand is uncertain. Now, in the previous video you have learned that we model this uncertainty by considering the observations as realizations of independent random variables with the same probability distribution, the so-called model distribution. You have also learned how to use the observations to get an idea about particular features of this distribution. In the example on the heights of male individuals, the observations are modeled as realizations of independent random variables with the same normal distribution. The parameter mu of this distribution corresponds to the typical height of a male individual, and you have learned that this can be estimated by the average of the observed heights. Now, more often, an unknown quantity of interest is represented by some parameter of the model distribution, and one wants to estimate this parameter by means of the observations. As you will see, it will not be difficult to come up with different estimators. This then raises the question which estimator is the best. And this, in turn, calls for criteria to assess the performance of an estimator. Now, to get a feel for what criteria are useful, let us consider a particular estimation problem in more detail. We go back to a situation in the Second World War in which the Allied forces wanted to get reliable estimates about the German war production. In order to do so, experts started to analyze markings and serial numbers obtained from captured German equipment, such as tires from German aircraft shot over Britain and tires from supply dumps captured in North Africa. After decoding the markers and serial numbers, it was possible to match each serial number with one of the main manufacturers and pinpoint the year and month in which the tire had been produced. Now, this meant that given the manufacturer, month and year, each tire was giving a serial number starting at 1, 2, 3, and so on until a largest unknown number, say K. The corresponding dataset of captured serial numbers could then be represented as numbers x1 up to xn, being drawn without replacement from the numbers 1 up to k. Now, this means that the estimation problem can be simplified to having an urn containing an unknown number of balls from 1 up to k, from which we draw without replacement a couple of balls with numbers x1 up to xn. And now the question is how to use the observed numbers to estimate k. Now let us think of a reasonable estimator. Now the average of the numbers in the urn is equal to the sum from 1 to k divided by k. Now from calculus, we know that the sum in the numerator is equal to k times k plus 1 over 2. And therefore, the average of the numbers in the urn is equal to k plus 1 over 2. Now suppose we have drawn numbers x1 to xn from the urn with average x bar. Because the observed numbers are drawn with equal probability, one might expect that the average of the observations is close to the average of the numbers in the urn. So one might expect that x bar is close to k plus 1 over 2, or equivalently, 2 times x bar minus 1 is close to k. Now this gives us a first reasonable estimator for k. Now here is another heuristic argument that leads to a different estimator. Note that all the numbers in the urn are spread equidistantly between 0 and k plus 1. 2 successive numbers in the urn are always at the same distance. And now, because the balls are drawn with equal probability, one might expect that the distance between 2 successive numbers drawn from the urn are also roughly at the same distance. For example, if we draw three numbers, their positions roughly divide the range in 4 equal parts. Now we use here the notation of order statistics as introduced in the MOOC on probability. So x brackets 1 is the smallest number and is roughly at 1/4 of k plus 1. The second order statistic is roughly at 2/4 of k plus 1. And the largest order statistic is roughly at 3/4 of k plus 1. And in general, if we draw n numbers, their positions roughly divide the range in n plus 1 equal parts, so that the largest order statistic is roughly at n over n plus 1 times k plus 1. Now this means that if we inflate the maximum with a factor n plus 1 over n and subtract 1, we end up approximately at k. Now you may stop the video here for a moment to check that the two statements are indeed equivalent. The previous reasoning leads to a second estimator, namely the largest number inflated by a factor n plus 1 over n minus 1. So to summarize, we have two estimators for the number of balls in the urn. T1 being the doubled average minus 1, and T2 being the inflated maximum minus 1. Now, to investigate how the uncertainty in drawing the balls affects both estimators, we run a small simulation in R. Suppose that we have an urn with 1,000 balls. We draw 10 balls from this urn without replacement and compute both estimates based on these 10 numbers. And we repeat this procedure 10,000 times to see the effect on both estimators. Now we can simulate the drawing of the balls by using the R command sample. And in this case, the R command sample draws 10 numbers without replacement from the numbers 1 to 1,000. Now running this code produces a dataset X consisting of 10 numbers. And for this dataset, we find the value of estimator 1 and the value for estimator 2. Now, if we repeat the whole procedure, it's very likely that we will find 10 other numbers, and therefore also other estimates. Now, we investigate the behavior of the estimators by repeating this a lot of times. 10,000 times we draw a dataset of 10 numbers without replacement from the numbers 1 to 1,000 and compute both estimates. Here's a histogram of the 10,000 values for estimator 1. We see that the variation in the possible outcomes for drawing 10 numbers without replacement results into variation in the estimates. Sometimes the estimate is too large, sometimes the estimate is too small, but on average the estimator is on target in the sense that the 10,000 estimates vary around the value 1,000. In fact, the average of the 10,000 estimates is indeed close to 1,000. Here is an histogram of the 10,000 values for estimator 2. We see that the variation in the possible outcomes for drawing 10 numbers has a completely different effect on estimator 2. Again, the estimates vary around the value 1,000, but in a different way than estimator 1. Nevertheless, the average of the 10,000 estimates is again close to 1,000, illustrating that also this estimator, on average, is on target. Well, after seeing both estimators at work, which estimator do you think is the better one? Well, you might pause the video for a moment to give this a thought. Have you made up your choice? Most people choose estimator 1, usually because the histogram looks more familiar. However, I was a bit cheating, not showing the information on the horizontal axis. The performance of both estimators can be compared best if we plot both histograms on the same scale. We then see that estimator 1 has a much larger variation around 1,000 than estimator 2. Now, since both estimators on average are on target, estimator 2 shows to be much more accurate than estimator 1. Now, the previous simulation was for drawing 10 balls out of an urn with 1,000 balls. Can we expect a similar performance of both estimators if we change the setup? For example, drawing a different number of balls or changing the amount of balls in the urn. Now, of course, we cannot check this by just running simulations in R, because there are infinitely many options. So this calls for a more mathematical approach to assess the performance of estimators in general. Well, this will be made more precise in the next video. Well, finally, let us return to estimating the German war production. With a sample of about 1,400 tires, individual output figures were obtained for almost all months over a period from 1939 to the mid-1943. Estimator 2 was used for this purpose. This table shows the accuracy of estimator 2 for the average monthly production in the first quarter of 1943, together with the statistics of the Speer Ministry that became available after the war. As you can see from the table, the estimates are quite close to the true values. Now, the accuracy can be appreciated even more if we compare them with the figures obtained by Allied intelligence agencies. Using other methods, they estimate the production to be about 5 times larger. This brings us to the end of video 1 of this week. In the next video, we will introduce 2 general mathematical concepts that measure the performance of estimators. See you then.